When an industrial crane hoists a concrete block weighing several tons, the tension is almost audible. The steel cables don't just hold the weight, they snap tight, adjusting to the massive gravitational pull. You can see the same effect on a larger scale beneath a highway overpass. As a loaded semi-truck passes overhead, the massive steel I-beams supporting the roadbed physically bow under the pressure. This happens in nature too. In a circus human pyramid, the performer at the very base supports the combined mass of everyone above them, their own skeletal structure compressing to keep the group balanced. While we treat materials like steel, concrete, and bone as if they are perfectly rigid, they are actually in a constant state of flux. Every solid object will stretch, compress, or bend when the applied force is high enough. The property that allows these materials to survive that pressure is elasticity. It is the ability of a solid to deform under a load and then return to its original shape and size the moment that force is removed. Designing safe structures requires accounting for this invisible movement. Understanding why a steel beam bends instead of breaks is the foundation of modern engineering. Engineers map the limits of these materials using a standard tensile test, pulling a metal cylinder apart with increasing force. The material develops an internal restoring force. This resistance is stress. The physical stretch is strain, calculated as the fractional change in length. On a stress-strain graph, the initial linear region obeys Hooke's law. Deformation is proportional to force, and the solid behaves elastically. But every material has a limit. Past its yield point, it enters plastic deformation and is permanently warped. Yield strength serves as a structural speed limit. For an engineer, crossing this threshold means the material has suffered permanent, irreversible damage. In the real world, materials face forces from every direction. Wind twists them, gravity crushes them, and shifting loads pull them sideways. To account for these different pressures, engineers use specialized ratios called elastic moduli. Young's modulus measures resistance to lengthwise stretching, the ratio of tensile stress to longitudinal strain. Steel's exceptionally high Young's modulus requires massive force to produce a tiny change in length compared to aluminum, explaining its dominance in heavy industry. When forces push parallel to a surface, like a sideways load on a pillar, the material undergoes shearing strain. The opposite faces of the object slide against each other at a specific angle. We calculate this resistance using the shear modulus. For most solids, this lateral strength is much lower than their lengthwise strength, often only about 1/3 of their Young's modulus. There is also the bulk modulus, which describes how solids resist uniform crushing from all sides, like deep-sea pressure. Because the atoms in a solid are so tightly coupled, they resist this compression far better than liquids or gases. By combining these different moduli, engineers can predict exactly how a chosen material will respond to the complex, multidirectional forces of the real world. These microscopic principles are what allow us to build on a macroscopic scale. Applying Young's modulus allows a designer to determine the exact cable thickness needed for a crane. They ensure the operational stress remains well below the yield point, keeping the steel safely within its elastic region. It also explains why infrastructure looks the way it does. Bridges use I-beams, because that specific shape is engineered to resist bending and shear stress while keeping the structure as light as possible. Even the human body follows these rules. Under a 220-kilogram load, a human thigh bone compresses by less than 1/10 of a millimeter, acting as a biological spring governed by its own elastic modulus. Engineers must also distinguish between ductile materials and brittle ones like glass. In brittle solids, the yield point and the fracture point are nearly identical, meaning the material will shatter suddenly without any warning deformation. Modern skyscrapers and bridges stay standing because every instance of their inevitable bending and stretching is predicted long before construction begins. We build higher by understanding the hidden, elastic nature of the materials beneath our feet.